All right. In this video stream, we're going to build a scheme-like interpreter in Go. We're going to call this scheme. So when I build these interpreters, well, we're going to start with an interpreter. We might extend it later into compiling to a bytecode VM. Might also extend it into compiling, probably to Go again. But anyway, in the first place, we just want to get a front end working. So the front end is the parsing part where you got lexing, you break the input programs into tokens, and then from there you have a parsing step where you take tokens and you put them in, turn them into an AST. So in our lexer first program we've got here, yes. Here's where we're going to want to be able to take an input source, which will make it easier on ourselves and just do an array of bytes. And the result of this is going to be a list of tokens. And a token is basically the actual string that you capture. We'll call it the value. It's going to have a type. Type, which we're going to do this. Also, yeah, I forget. We don't need to make these public for now, so let's make these all private. So token is going to have a, okay, yeah, but it's Go, so you can't call it a type. You have to call it something like kind, and we'll call this kind here too. And Go doesn't have enums, so instead of enum, we do the trick with iota. And for now, the token kinds that we're going to want to think about are syntax tokens. Syntax token. And identifier token. And let's do numeric token. It may be better to break these out into integer or float. I haven't made up my mind about that yet. Let's do integer token for now. And then, all right, so each token that we produce from lexing the source code, so let's type out what we want to see here. So again, we're building an interpreter for a scheme-like language. It doesn't really matter if it's interpreting right now, we have to do the front-end part, which is parsing it and lexing it first. But if this is a scheme-like language, we want to be able to have something like this. And in the lexing stage, all that should do, if this is this is like the contents of a file, that string there. After lexing that, we should have something like this. So we've broken out each of their individual into the smallest string components that we have before we get into lexing. And just to make this a little stand as well, like we have to be able to group compound characters together as well. All right, so that's what should produce. All right. Also, I'm going to turn off the shield mod for a second because I just realized that that's going to ban anyone from talking at all for now. And if there's a need to, then I'll figure out how to turn that back on. Okay, so now that we've got this, the basic logic inside of Lex is going to be that we've got our token list that we're going to want to accumulate. And then somewhere in here, we're going to be iterating over all the characters in the source. Characters is... Oh, yeah. We can be a little bit more Unicode friendly if we act on rune lists rather than byte lists. So one cool trick in Go is that if... I'm pretty sure about this. If you have a string and you cast that to a rune array, you get it broken out by all the runes in it. And the reason that we want to think about runes rather than bytes is that in Go, runes represent individual Unicode. I always forget what the name of it is, but the smallest individual thing that is valid in Unicode. So if it was like a Chinese character, it would be the whole Chinese character. That would be a rune. Whereas the actual encoding of it is going to be a couple of bytes. It's going to be like 3 or 4 bytes. So we don't want to think about arrays of bytes. It's nice that Go lets us think about array of runes. And all we have to do to get the array of runes is just cast some string to an array of runes. And then it will do that whole logic of breaking it up, even though the bytes inside of it are variable size. All right, so inside of this lex function, we're going to want to do a couple things. We're going to want to eat white space. We always want to do that. So let's add some white space to this example as well to show what that would mean. Well, there already was white space in there, so you get the point. But even this shows a little bit more that you want to be skipping on the white space. All right. So yeah, one of the things we're going to want to do inside of here is eat all white space. By eat, I just mean drop it, basically. And then we're also, inside of here, we're going to want to check if the current set of runes that we're currently looking at if it is a syntax token, which is going to be stuff like these left and right parentheses, an identifier token, which is going to be all characters for us that are not syntax and not numbers. So basically that's just stuff like the plus sign, or if we had some built-in function called add, then it would be things like that. So let's add examples of these up here. Syntax wiki. All right. Code points, yeah. I should memorize the terms sometime, but until now, I'll count on people commenting at me to let me know. Thank you. All right. So check for syntax token, or check for integer token. And let's just reorder this everywhere. If we put the identifier token checked to last, then we just get to have a little bit less logic, because we can just say if it's anything else that is not white space, basically, then it will be an identifier token. And after each of these, we like if they are one of them, so we need to continue. And we were going to accumulate that token that we get from there. All right, so let's... all right, so the other thing that I haven't introduced is this concept of cursor. We're going to be making our way through the source string, and a convenient way of doing that is by having a cursor that tracks where we're currently looking at in the source rune array. So all of these functions are going to get the source rune array, and they're going to get the cursor, and they're going to return a cursor, and they might return a token. And they might also return something that says whether anything was found at all. That way we can keep going down through these other checks if we need to. So we're going to say cursor equals white space source cursor. That one should be pretty easy. It's not going to return. Oh, yeah, it does need. It needs to return the cursor. All right, so inside of here, we'll do another iteration, which is for cursor less. Oh yeah, we should probably do that here too. For cursor less than lane source. Source if source if this is one of these white space characters. But actually, since I mentioned that in this other one, identifier token. Identifier token is also going to need a check for white space, so let's have a is white space function. And then we don't really need that C anymore. If it is white space, then cursor plus plus continue, otherwise break, return cursor. All right. It's always hard to tell when you're doing this stuff live or in an interview when you're getting incredibly stupid logic mistakes wrong. And my only solution is to do unit tests. So once this is a little bit further done, I'll add some unit tests to make sure that I'm not going insane. Or you'll catch it and let me know. All right. Is white space R rune. I think that there actually is a. Oh yeah, maybe there's a Unicode is white space in the Go standard library. I think. Let me check. Code. Yeah. Maybe we can just use that instead. So if we didn't have that, then it would just be checking like, is the thing an empty space, or is it a tab character? Is it a new line character? But since there's a built-in function that will tell us about this, and it will be broader than those because there are more Unicode space characters than just the couple of ones that I just mentioned to you. That I only know the ASCII ones, and I'm not even sure I know all of them. All right, so we iterate through it as far as we can, and if it is a space, we increment the cursor and continue. Otherwise, as soon as we don't find a space, we break. All right, that seems reasonable. Okay, we've done is white space. Now we can do syntax token. So one of the things that I like to introduce now is a greatest match function. Because this is gonna, well, no. Yeah, it's only necessary for syntax token in this case. I forgot. All right, maybe we don't need that. I don't know yet. We'll see if we need that. Let's do lex syntax token. So like everything else, it needs to take the source, it needs to take the current cursor, and it's going to return at least the cursor. So the next function here, or we're going to assign to it basically. It's going to be something like this, something like syntax token source, so that we can keep propagating the cursor as we lex through the string. And other than that, we could return a token pointer. And the point of doing this is that if we only use nil to say that that nothing was lexed. There are a bunch of different ways that we could do it. Like we could set cursor to -1, and then this would say right here, if cursor not equal to -1, then we know that it was a good one. But I don't know. In languages that have optional types, this is what they're used for, but Go doesn't do that. So, or the other option would be that we have a third bool return value, and we would check that, and that would tell us whether or not the lexing was successful. But I don't know. It's annoying to have another return. So we'll just do this, I guess. And right now, since this is such a simple language that we're getting started with, we don't even have to do anything that intelligent. We can just do this. When you're lexing more complicated languages, well, I mean, this might get more complicated. No, in a scheme when you have only S expressions, I don't think it actually gets more complicated than that. Those are the only special characters. It would just be if you're doing common Lisp reader macros. I mean, that would just be a whole another level of insanity. So this is probably sufficient. If it is one of these, then we'll return cursor +1 because we need to get rid of that token that we're reading right now. And see, what were the value and kind? Value is source cursor. Okay, this is kind of annoying. Yep, just a basic scheme. It's my first video, so I'm just going to keep it very simple. All right, value and kind is syntax kind. And now that I see this, the other stuff that we're missing here is location. So yeah, let's at least store the current cursor. And it's always super useful to have some kind of, I don't want to do this right now, but we might need it by the end of the time that I finish recording this video, a debug function here where this takes in the original source code. And based on the token and based on its location, you want to be able to have a nice printout in case of errors, basically. You want to be able to say, here was the line number, and here was the actual line source code, the line number, and the actual character position. It's always really nice to have those. So maybe we'll implement this in this video. All right, well, at least we're tracking location now, so that's good. Otherwise here, okay. So this reminds me too that even when because of how we did these assignments here, we need to make sure that we're returning something safely here, because if we're going to have this assigned when this function returns, whether or not this function succeeded in lexing the token is trying to succeed, the cursor needs to not go to the wrong place, basically. So we're going to always return the cursor of where it started, and that's all we're doing here. So this, that's cursor and token. Let's give ourselves a token we can work with. Right. So now this, all right, so here is where we've got a successful lexing of the syntax token, and we need to accumulate that token kind, and then we can continue. that looks fine. Okay, so now that we've got the syntax tokens, let's do, which one's next? Integer tokens. The same thing, cursor t integer token. No, oops, not equal now. And since it's a pointer, I just realized we need to dereference it there. Tokens equal. All right, so for this one, let's copy the signature here. For this one, we're going to iterate as long as we need to. And we're going to accumulate the entire integer token. So if this isn't a valid one, but if the input is this isn't a valid program, I mean, but if the input is this and the cursor is 0, 0, 1, 2, 3, 4, then this should produce 1, 2, 3. And just another example. If that was a cursor, then this should produce 1, 2. So, and it's not based, well, you get into weird things where you have stuff like this. And I think I'm just going to ignore that case right now. It's probably better to deal with it here in the future. If this were a serious language, it would probably be good to deal with this at the lexing stage and say you can't have 12a. That doesn't mean anything. But just to keep it simple, I'm going to ignore this one. So this lets us say if the character is not alphanumeric, if the character is numeric, if r and we need to have the accumulator here, or we can just make a token. No, let's not do that because we want this to be, because we were dealing with an array of runes, let's accumulate as an array of runes. So the value is an array of runes, and our continue. Otherwise, we can say here that if you didn't get into that situation, then we'll break. And here we'll say if the val length is 0, then we failed. Otherwise, we're going to return, and I just realized we weren't keeping track of the cursor. We weren't incrementing it here. And if we're incrementing it and we still need to be able to return potentially the original one, then that means we're going to have to keep track of this separately. So let's have an original cursor. So if we ultimately did not accumulate anything, we did not find an integer, then we're going to return the original cursor and nil. And if the value is not nothing, then we're going to return the new position and a token. And the kind is integer token. And one thing that I always get wrong is here, is this supposed to be cursor or cursor plus 1? But we'll catch that in unit tests. So I'm going to not think about that further for now. And lastly, we've got the identifier token. So all that looks fine. As a final catch, this is where we want to have something like that debug function. So we got to something that is not valid. So for now, let's just panic. And we should improve that pretty quickly. With unit tests, it'll be more obvious because we can control it more easily, but when you're just entering random stuff in, or when you're programming against a language implementation like this is where you want that debugging lines of source code. So we would like to be able to do grab the last token and debug it here so that we can say, here's the line of code and column in that line of code where we stop being able to lex. All right, but for now we're just going to panic, and we need to implement that identifier token. So this one, like I said, we can simplify this for now and have it be, we don't even really need to do an example. While the cursor, if it's not white space, then we're going to say that it's a valid identifier. And here we'll do the same kind of thing that we did over here, where we need to accumulate all these runes that are part of the valid token. And if we're incrementing that cursor, we're going to need to keep track of the original in case fails. And after this, continue, otherwise break. So now we'll just copy all this logic. It's the same. If we did accumulate anything in here, if we did find valid runes that were part of an identifier, then we're good, which is this section here, but it should be identifier. And otherwise, if we didn't, we've got that original cursor case. All right, but just to show the examples of what this means, let's identifier. This is 4 again, then this should produce AB. And actually, based on the logic right now, if this was AB123, it would also produce that, because right here we're only checking if the token is not a space character or rune. And that's that in this situation, that seems fine even in the long term, because most languages are okay if you have a number that's part of an identifier. It just isn't supposed to start with it. Okay, so we are done lexing already. That was quicker than I thought it might be. Let's write some unit tests for this. And since we already wrote these examples here, let's just copy these over. Test lex token. And I always use one of the expect packages, so I can't even remember how we do this. I'm going to look it up. I know the Google style guide says don't use expect packages or anything like that, but I really don't like Go's testing library on its own. I don't like how you have to do all the comparisons yourself and then just call fatal. That's always really annoying to me. So what do I use? A certify? Expectify? What's it called? Testify. Yeah, that's the one I like. All right. So other than this, we won't be using third-party libraries, but this is just for testing. And let's see, equal. We're not going to be able to just call let's integer token because it returns a tuple, and Go doesn't actually support tuples as expressions. So let's make a set of tests. Input source cursor. No, I'm not scared of Copilot, but I'm indifferent or annoyed by it. All right, this is my fault. I turned off the shield thing, and this is what I get. How do I deal with it? So you can ban people, you can block people, but you can't delete their messages. All right. Source cursor and yeah, expected output. So one of these, 2, 1, 3, cursor is 4. I expect this to be 3. 2, 12, 3. Expect that to be 12. And this one, that's to be 12A. Cursor token equals token test dot source test dot cursor and cert equal cursor. Oh, okay. Yeah, well, yeah, we should test that. Expected value and expected cursor. So this one, I guess the cursor should be 7. This one, the cursor should be 6. And this one, 7, because the character lengths were 3, and then 2, and then 3 again. Cursor. What did I do? And while we're testing stuff, we can also expect that the token kind is an integer token. All right, this is the first time trying to compile this one, so let's see what happens. Go mod init live scheme go 90. All right, tons of syntax errors. Let's see what $43. Oh yeah, okay. I I can't do that. So I started up the thing by calling these capital token, but then I decided I didn't want to export it. But I can't just rename them all. And since I'm just using Emacs, I can't do a. I don't even know how to do a identifier find and replace. So let's look for where this was. Now, what are you? Oh, kind. Okay, syntax token. Okay, well that's the first two done. All right. Line 75. Okay. Yep, these all need to be pointers. 103. Lex syntax token is type token and assignment. 120. Right. This temporary one. Okay. And that's right. These are not called token. These are called P. Ah, yeah, good point. Did not return the tokens. Okay, cool. Let's give this a name. Just make it happy. All right. Well, we're done with the syntax errors now. Let us try those tests. And now there's test syntax errors. Can I use test.source as type rune? Right. We need, so lexing, like I said in the beginning, we want to act on rune arrays all the time because that lets us iterate over like Unicode code points, I guess is what they're called, rather than string characters. Can I forward running go test under a watch command every few seconds? Probably. There was a time like 5 years ago or 6 years ago that I used to do watch commands for JavaScript projects, but I never really got into it, so I just run it manually. Most of my workflow is pretty manual. All right, so we got actual test errors now. Not equal 6 to 7. All right, the one annoying thing about these Go test table things is that they get kind of hard to find which test is failing. So I'm going to print out the source. Or let's just print out the entire test. But then that doesn't even really help very much because they're not in line with the actual failures. You get all the print lines up here at the top, and then unrelatedly, you get all the error failures down here. Okay, well that's one that I'm noticing right here. The second one, there's a way to name each step. If that's true, I don't know it. Yeah, so this one, this previously I incorrectly, yeah, so naming each test step, it depends on the assertion library. This is, I think, part of why the Google's Go style guide says don't use these assertion libraries because they don't let you name it. I don't understand why these assertion libraries just don't give you the final argument. Like in JavaScript packages, they often have a thing where you can have a final argument here that says like, I want to put something here. Actually, that would not even help me in this case because my problem is not which of these assertions is failing. My problem is that which input of these tests in this table is it failing on. Still, maybe there's a way to be more verbose about it, but I'm not sure how. Anyway, oh yeah, so oh, all right, that's annoying. So up here, originally I mistyped this and I said that this one, when we're lexing this one, oh, integer. Oh. Okay. All right. No, sorry. I'm getting the identifier lexing mixed up with the integer lexing. All right. Yes, this is correct. 12. And okay, good. This one should be 12 too because And this is the integer lexing part, not identifier lexing. So we should be down to, oh, what? Oh, cool. I thought I was the only one. Oh, there we go. All right, this one's good. Let's see what else we've got in here. All right, let's do the identifier ones next. And we'll copy most of this code. And these are the cases that we want. Expect this one to be AB, I think, which would mean that the expected cursor is 6. And we expect this one to be AB123. And since it starts at 4 and this is 5 characters long, this should be 9, and we don't have a final. So, okay, great. We panicked. Let's get rid of these formats. We don't need these anymore. Format. All right, why are you panicking? Okay. Well, it gives one test gets through here. Oh, okay, okay. That it must be because we're accessing. Okay, all right. So the token is coming back as nil. This is. All right, I didn't rename that. All right. Wait, which one are we talking about? I didn't rename it down here. Okay, that's better. So now which this is line 71. The kind. Okay, great. Just I copy and pasted, and I did not change everything to be talking about identifiers. All right, great. This worked. So the identifier one is good too. So far, all the bugs have been in my tests and not in my source code, which is interesting. The syntax token. This one's so easy that I don't even really feel like testing it. So let's try just running tests for the actual lex function. So the tests here, there'll be an input, which will be a string again, and then there'll just be a list of tokens. So my input here, can't see much of the editor. Oh no. How does, oh, all right. Thanks for calling that up. I thought that I had the bottom of this lined up correctly, but I guess I did not. All right, I'll just stick to the top half of it for now and get this fixed up for another video. So that's our source. Then these. So one reason that I'm always lazy to do these unit tests, especially in the lexer and the parser, is because once you start doing parsing tests, you have to like, and it gets into a complicated program, and you're keeping track of location too. Then you've got this like gigantic list of tokens, and eventually like a gigantic tree that includes the location of everything, and it's just tedious. But this is a small program, so it's not gonna be that bad. Kind is syntax kind, location is 0. And oops, I forgot to. This one is plus. This could be an identifier kind. It's locate. Oh, all right. So if we got leading spaces, then now its location is no longer 0. Its location is 1. This one's location looks like 4, 0, 1, 2, 3. Its location is 3. The next two are numbers. $13, and next one is going to be 2. And then we've just got the ending parentheses. And what was its position? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. So now that's just the test case. Now we need to actually write the code for it. Tokens, lex, test by source. I wonder if I can just check if all the tokens are equal to what. What is the issue? What are you complaining about? Okay. So one thing we can do to make this easier is that we can accept a string here, and then immediately convert this to the array. That makes this a little bit of a nicer API while still giving us that rune array to deal with. Why are you still complaining? Okay, that's not a valid complaint, and this one, you're complaining to give you the T. And, okay, all these are not called kind, they're called token. All right. Undefined tokens. Right. It was just token. All right. Now, how low on that can you see? All right. Let's see. What's the issue? Locations. Which one are you having an issue with? Kind, location. All right, so this one is not lining up and this one is not lining up. The plus is not lined up. Three of these are not lined up. All right, plus 13 and 2 are not lined up. 0, 1, 2, 3. 0, 1, 0, 1, 2, 3. That sounds like it's a bug then, because this one should be at position 3. 0, 1, 2, 3. These get pretty annoying to debug because once you start incrementing incorrectly somewhere, then it just can get messed up everywhere. 0, 1, 2, 3. So that seems like it's likely, though, either white space that is not being correctly incrementing, or the syntax token, because those are the two ones that happened before this. This is white space here. This needs to get incremented and eaten up. And then we've got the syntax token here. And then the tester saying that this one is reported as position 4, whereas clearly 0, 1, 2, 3, it's at position 3. So let's look at the white space function again. While the cursor is less than lang source, check if it's the current cursor is source code. If it is, then increment the cursor. That seems right. And similarly, the syntax token is really simple. All it does is okay. All right, maybe this is the issue. Wait, no, that doesn't make sense. We return cursor +1, but we set the location to the original cursor. You know what? Okay, I think that I don't know. I'm confused. I realize another logical issue is that the location is supposed to be the original cursor always. So in all these places where we set up the original cursor, we need to always report back that the token is at that position. But I don't think that that's going to fix the issue because the plus came before the 13 and the 2. Let's try it. Okay, well, it says it works, so I'm okay. Maybe it was only complaining about these last ones, 13, 2, and the right parentheses. All right, so we've got a lexer that works. I think I'm going to stop there for this weekend. We can go into the parser next week. So basically, the next step is, now that we've got that list of tokens, inside of main, what we're going to do here is somehow accept a program. And well, let's just do that right now. Os.read file. Something like this. I'll probably get that wrong. Panic. Otherwise, we're going to lex that. And what's the issue here? Array of bytes? Yeah. Let's see. Okay, well, it built. Let's make an example file. Okay, you panicked. That's cool. That must be because of end of file character. Why would you panic, though? Where are you panicking? Line 42. All right, so we get into like syntax token. Okay. So there's no, so this does some, all the rest of these lex token helpers, they immediately continue. So we get to go back here and we get to fall into this case or not. But this one doesn't. So we need an extra condition here, basically. Yeah, there we go. All right. So we've got a very basic setup there, enough to do a lexing. The next step, which again, I'll say for another stream, is parsing. So this one is going to take that that list of tokens, and we're going to parse it. And then after that, we can do AST walking execution. Where maybe if some value is computed, and we can print that out. And in the future, we can have switches where instead of doing the interpretation of the AST, we can compile the AST to whatever we want. All right, but yeah, we got the first step down. We've got unit tests for lexing. And next time we'll get into the parsing. And after that, we can go into different ways of executing. See you around.